Hey, I'm Dhanajit Brahma, and today I'm going to present our paper titled A Probabilistic Framework for Lifelong Test Time Adaptation. In a nutshell, we propose PETAL, a probabilistic framework for lifelong test time adaptation utilizing a partly data-driven prior. The probabilistic formulation naturally leads to the student-teacher cross-entropy loss along with the regularizer. This regularizer corresponds to the posterior of source domain data. Moreover, we propose a Fisher information-based data-driven parameter restore mechanism, and experimental results demonstrate that PETAL outperforms current state-of-the-art approaches for lifelong test time adaptation across various benchmark datasets. Let's dive deeper into the details, starting with a little bit of background and introduction. In real-world scenarios, we observe a domain shift between the distribution of source domain training data and target domain test data. Moreover, source training data may not be available in practical scenarios due to privacy and legal constraints. It is also observed that deep neural nets make inaccurate prediction and unreliable uncertainty estimates in the presence of domain shift. Test time adaptation is one way to robustify deep neural nets. In test time adaptation, we adapt the source domain pre-trained model by learning from unlabeled test data. Since real-world machine systems work in non-stationary and continually changing environment, lifelong continual TTA becomes a problem of significant interest, but the target test domain distribution changes over time. Let's describe the setup more formally. We are provided with a pre-trained model theta 0 trained on source domain data X, and we have unlabeled target or test domain data coming from multiple domains. In test time adaptation, we adapt from the source pre-trained parameters to the test domain specific parameters separately, whereas in lifelong test time adaptation, we start from the source pre-trained model and continually adapt to data coming from different domains with no information about the change in the domain. In the related prior work, Dent adapts the pre-trained model to test data by updating trainable parameters in batch norm layers using entropy minimization. Batch provides a Bayesian perspective for test time adaptation that naturally gives rise to a regularizer. In other words, batch can be seen as tent along with a regularizer. Moreover, it computes the approximate source posterior during the training time itself. CoTTA continually adapts the pre-trained model to various target domain test data. It has a self-training framework that maintains weight average teacher model. Moreover, it utilizes the augmentation average prediction to improve the quality of pseudo labels. Further, it uses stochastic or random restore to avoid performance degradation in the long run. Let us now delve deeper into our proposed approach PETAL. We address the problem of lifelong test time adaptation from a probabilistic perspective. OTTA arises as a special case of our probabilistic framework. Posterior for source training data leads to a regularizer term in the learning objective. The probabilistic perspective naturally gives rise to the student-teacher self-training framework along with the regularizer. Moreover, we propose a data-driven Fisher information matrix-based parameter restore to improve upon stochastic restore. Our principled use of an approximate training posterior surpasses prior heuristic approaches. Our probabilistic formulation leads to better uncertainty estimates. This is our proposed probabilistic framework PETAL for lifelong test time adaptation. We obtain a source domain pre-trained model from the posterior density learned using training data from the source domain. The posterior density is used to initialize the student model. A test sample is provided as an input to the student model. Using multiple augmentations of a test sample, we obtain augmentation average prediction from the teacher model. The loss term consists of log posterior and cross entropy terms utilizing student and teacher model predictions. We utilize backpropagation to update student model and exponential moving average for teacher model. We propose a formulation of Bayesian semi-supervised learning with student-teacher model. The prior is partly defined from the data, as we have a cross-entropy based partly data-dependent prior that utilizes prediction from the teacher model as well as the student model. Having teacher model as the exponential moving average helps in combating error accumulation and catastrophic forgetting. Further, we propose a formulation for handling covariate shift with student-teacher model, resulting in an additional factor in the partly data-defined prior for covariate shift. This is the final learning objective. The Q theta is an approximate posterior learned during the training itself. We obtain the adapted parameters by optimizing this objective. Following backs, we use swag diagonal for posterior approximation. In order to handle catastrophic forgetting, we propose a data-driven parameter restore in order to improve upon random restore. Specifically, we utilize FIM of student model parameterized by theta. We consider the diagonal approximation of FIM. Using this, we get the threshold value used to compute mask for determining which parameters to restore. Experimental results demonstrate the efficacy of our proposed approach PETAL. PETAL performs better than other approaches in terms of error rate at corruption severity level 5 for CFAR 10 to CFAR 10C as well as CFAR 100 to CFAR 100C. For ImageNet-C, we report results averaged over all corruption types and over 10 diverse corruption orders at the highest corruption severity. The performance per corruption is depicted here, and we can see that PETAL does well for all the corruptions. We also experiment on ImageNet 3D-CC, and PETAL outperforms other approaches here as well. To summarize, our work focused on the problem of lifelong TTA. We addressed the problem of lifelong TTA from a probabilistic perspective. We proposed a novel approach PETAL that naturally gives rise to a student-teacher framework along with a regularizer and better uncertainty estimates. Additionally, our approach can be easily extended for Bayesian SSL when the labeled and unlabeled data distributions are not the same. Moreover, we developed a data-driven Fisher information matrix-based parameter restore, and experimental results demonstrate that PETAL has surpassed state-of-the-art results on various lifelong TTA benchmark datasets. Visit our paper for more details and insights.